Good morning, students. I welcome you all for the another session of this arches and cable structures. So, in the previous session, we have seen how to find out the length of the cable and other parameters. Now, let us take one more interesting thing in this cable structures. So, that is anchor cables and towers. Okay, so you can see here, this is called as a suspension cable. Okay, this suspension cable will going to pass through this pulley, and this side there will be a anchor cable. Now let us take this anchor cable and this tower. So tower is nothing but this is a support in which the cable is suspended. So this side it is a suspension cable and this side it is a anchor cable. Okay, so the suspension cable is supported on either side on supporting towers. So this suspension cable is supported on this tower. The anchor cable transfer, okay, this is the anchor cable. The anchor cable transfers the tension of the suspension cable to the anchorage consisting of huge mass of concrete. As you know already, there will be a tension force in the suspension cable. So this tension will be transferred to the anchor cable. Okay, so whatever the tension is there, this will be transferred to this anchor cable, and in turn this anchor cable will transfer the tension to the here a big concrete mass will be there. Okay, this is what the process we'll going to see. So the tension in the suspension cable will be transferred to this anchor cable, okay, through this pulley. Okay, so there are two ways we can transfer this tension in the suspension cable to the anchor cable. So the first method is the suspension cable can either be passed over the guide pulley for anchoring it. So this is the first process in which the suspension cable will be there, and whatever the tension is there in the suspension cable, it will be transferred to this anchor cable through this pulley. So the pulley will be provided over this, the cable will going to pass. Okay, now this is suspension cable, this is anchor cable. Whatever the force in the suspension cable is transferred to the anchor cable with the help of this pulley, that is smooth pulley. Okay, or the second way is the suspension cable can be attached to a saddle mounted on rollers. The second option is this. Okay, this you can see the cable connected to the saddle. Now here same tower will be there. This is the suspension cable and this is the anchor cable, but here pulley will not be there. This arrangement is called as saddle. Okay, this is called as saddle, which is mounted on the rollers. So over the tower rollers will be there, and over the rollers a saddle will be there, and each end of the saddle is connected with suspension cable and anchor cable. So let us take first arrangement. So that is a cable passes over the smooth pulley. So this is a pulley. Okay, a wheel, what you can say that this is a pulley, smooth pulley. So there will be no friction. Okay, it is a frictionless pulley. So one end is a suspension cable and the same cable will be passed through this pulley, and this is called as anchor cable. Now when the see here, so this is the tension in the suspension cable and this is the tension in the anchor cable. Now this force and this force will be same because of this pulley. Okay, so since it is a frictionless or it is a smooth pulley, the same force will be there in these two cables. This is T means this is also T because of this frictionless pulley. Now you can take this this as the T force. So this can be, now see, this cable, suspension cable, is making an angle of theta with the horizontal. So suspension cable is making an angle of theta with horizontal. Okay, and anchor cable is making an angle of alpha. Okay, anchor cable is making an angle of alpha with the horizontal. This is theta, this is alpha. Now if you take this force, tension force T, I can resolve this into horizontal. So this theta is nothing but this theta. So you can resolve this along horizontal. Horizontal means it is T cos theta and vertical means T sin theta. Okay, similarly the tension force in the anchor cable So this is making an angle of alpha here. So again, if you take this T, okay, tension in the anchor cable, even this can be resolved into horizontal and vertical. Now this is T cos alpha and this is T sin alpha. So remember this figure clearly, important it is. Now when the suspension cable, this is a suspension cable, passes over the smooth pulley, okay, then this tension will be transferred to this anchor cable. Because of this smooth pulley, this T and this T, that is tension in the suspension cable and tension in the anchor cable will be same, that is on both sides it will be same. Let theta be the angle made by this suspension cable with the horizontal and alpha be the angle made by the anchor cable with the horizontal. Okay. Now see here. Now assuming the pulley is frictionless, means there will be no friction in the pulley. Okay. Tension in anchor cable is taken same as the tension in the suspension cable. Same. Okay. Now let us observe this sketch. Same sketch I have drawn here. So this is the tower. Okay. Over this pulley will be there, and this is the suspension cable T. Only you can take suspension cable T, tension, that is tension in the suspension cable. As usual, we are going to resolve this with help of this theta. So this horizontal component will be T cos theta and vertical component will be T sin theta. And this is the height of the tower. This is small h. Okay. Now what is the vertical load transmitted to the tower? So what will be the vertical load on this tower now? Again, you can take this is also. Now in this case, you have taken suspension cable. This side what is there? That is anchor cable will be there. So same, this is also T, this is also T. Okay. Now again, anchor cable will be making an angle of alpha with the horizontal. Okay. So similarly, I can resolve this T along X and along Y. So along X, what is the component? This is T cos alpha. T cos alpha, and resolve this along vertical, it is T sin alpha. Okay. So here it is taking suspension cable, here it is taking anchor cable. Now let us derive these two things. One is what is the vertical load transmitted to the tower? So what will be the load on this tower? Vertical load, I am talking about vertical load. What will be the vertical load on this tower now? When the suspension cable is considered, what is the vertical load? This is T sin theta, correct? So for this T sin theta, and for similarly, what is the vertical load due to this anchor cable? It is T sin alpha. Okay, T sin theta, and this is T sin alpha. T sin theta is because of this tension in the suspension cable, and T sin alpha is because of tension in the anchor cable. So both are acting vertically down to the tower. Okay. Now therefore, what is the total vertical load transmitted to the tower? From this it is how much? T sin theta, and from this it is T sin alpha. So therefore, on the tower, okay, on the tower, because of the suspension cable and anchor cable, what will be the vertical load? Okay, that is T sin theta here and T sin alpha. Both are in the same direction, downward direction. We can take plus, that is a T sin theta plus T sin alpha. Okay, this is vertical load to the tower. Then similarly, what is the horizontal load to the tower? Similarly, what is the horizontal load to this tower and this tower? Okay, so horizontal load, what is here now? It is T cos theta. Okay, T cos theta, and from this it is T cos alpha. Now see, this is moving in this direction, this is moving in this direction, means I can take T cos theta minus T cos alpha. Okay, so these T cos theta minus T cos alpha will be the horizontal load transmitted to this tower, and this is what? T sin theta, okay, T sin theta plus T sin alpha will be the vertical load transferred to the tower. Okay, this is important expressions you can remember. Now what will be the bending moment on this tower? What will be the bending moment on this tower? We are going to consider. Okay, so bending moment on the tower, is equal to, okay, horizontal force on tower into height of tower. Okay, what is the horizontal force? From here, what is the horizontal force? It is T cos theta, and from this, what is the horizontal force? T cos alpha. What is the bending moment here now? What is the bending moment here now? Because of this will go into 0 now. Okay, this will going to pass through tower only. There is no bending moment for this. So with reference to this, what is the bending moment? This is T cos theta into height h. So we are calculating bending moment at tower, bottom of the tower. So T cos theta into h, okay, is the bending moment. Similarly here, what is the bending moment at the bottom? It is a T cos alpha into h. Okay, so bending moment due to this is 0. Bending moment this is 0 because this will going to pass through tower only. So only the bending moment is due to horizontal load, that is T cos theta into h. Okay, and then this T cos alpha into h. So that's why you are written here bending moment at the bottom of the tower m is equal to T cos theta, okay, T cos theta into h, then minus whatever the load. This is the final horizontal load. Okay, so T cos theta minus T cos alpha will be the horizontal load into h. Okay, into h will be the bending moment at the bottom of the tower. Right, and note, important thing is this horizontal force will cause bending moment. So this horizontal force will going to cause bending moment, and these vertical loads will not going to cause bending moment because they are going to pass through the tower only. So there will be no bending moment due to these vertical loads. So vertical load will be bending moment will be due to this and this only. So this is the bending moment at the bottom of the tower, that is T cos theta minus T cos alpha will be the horizontal load into h will be the bending moment. Okay, now this is the first arrangement. So when the suspension cable, okay, when the suspension cable passes over this smooth pulley, okay, remember the condition is it is passing over the smooth pulley. So there will be vertical load, that is T sin theta plus T sin alpha, that is vertical load, and horizontal load will be T cos theta minus T cos alpha, that is the horizontal load, and bending moment at the bottom of the tower is T cos theta minus T cos alpha into h. Okay, now second condition we will going to take cable connected to the saddle or roller. So see this condition. So same tower, this is suspension cable, this is anchor cable, but see here arrangement is like there is no, okay, pulley like this. Pulley will not be there. So over the tower rollers will be there. Over the roller this saddle, this is called as a saddle. Okay, so the saddle will be provided. So one end of the saddle is connected to suspension cable, another at another end it will be connected anchor cable. Okay, now same thing, the suspension cable will going to make an angle theta, okay, and anchor cable will going to make an angle of alpha here. Okay, same thing, the force in the suspension cable is T, that is tension force. Again we can resolve this T cos theta, T sin theta. Similarly here, now I can write it as T1. So this is T, this is T1. These two are not same. Okay, here this is also T, this is also T because of this smooth pulley, frictionless pulley. So there is no pulley here. So tension in the suspension cable is different, tension in the anchor cable is different. Here tension is T, here tension is T1. So I can resolve this T1. Horizontal is T1 cos alpha, T1 cos alpha, and this is T1 sin alpha. Okay, right. So next, if the cable is supported on saddle and the saddle is mounted on rollers, the horizontal components of the tension in the suspension cable and in the anchor cable will be equal. Okay, horizontal force will be equal since the rollers do not have any horizontal reactions. So since it is a roller, okay, rollers are provided here. So since the rollers are there, so no horizontal reactions will be there, only vertical reactions will be there. So therefore this suspension cable and anchor cable will going to be considered now. Okay, assuming saddle to have frictionless rollers. Now similarly we can assume these rollers having frictionless, means smooth rollers will be there. Okay, now again resolving this, so minus t cos alpha. Now see the same thing, two diagrams you can observe here. This is for suspension cable, this is for anchor cable. Okay, so now here what is the horizontal component? Okay, so here it is t cos alpha, okay, and here it is t cos theta. Okay, I can take this is minus, okay, minus t cos alpha plus t cos theta. If you resolve horizontally or summation fx, what you can say that. Okay, so this is minus t cos alpha, this is alpha now, okay, minus t cos alpha, and this is plus t cos theta, that is equal to 0. Okay, horizontal summation fx is equal to 0 because of this frictionless rollers. So now t1 cos alpha is equal to, you can take this term this side, so this becomes plus t1 cos alpha is equal to t cos theta. Okay, you can find out t1, so therefore t1 is equal to t into cos theta divided by cos alpha, cos theta divided by cos alpha. What this expression gives, now see what is t1. Okay, T1 is nothing but the tension in the anchor cable, remember. So this equation gives tension in the anchor cable, means here these two are not same here now. T we can find out, but what about T1? So T1 we can find out from this equation. So T1 is equal to T into cos theta divided by cos alpha. Okay, so since the saddle is having frictionless rollers, right, there is no horizontal force, remember there is no horizontal force, and hence no bending moment on the tower. So for this arrangement, that is a saddle and rollers, for this arrangement there will be no bending moment because of no horizontal reactions. Horizontal reactions is equal to 0. So since there is no horizontal reactions, no bending moment on the tower. Okay, since the saddle is having frictionless rollers, there is no horizontal force and hence no bending moment on the tower. So therefore maximum bending moment on the tower is equal to 0. For the second arrangement, no bending moment on the tower, remember, and no horizontal reactions. Okay, so therefore only there will be only vertical reaction. So vertical force on the tower, that is only vertical force on the tower is equal to what? Here it is what? Okay, t sin alpha, here it is, sorry, t1, it is t1 sin alpha plus t sin theta. Okay, here t1 sin alpha plus t sin theta. So if you add these two, so these two, the summation will give the what? Vertical load on the tower, vertical load on the tower, and this is equal to this 0 because this is frictionless roller. So only there is, remember, for the second arrangement only there is vertical force on the tower. Vertical force on this tower is equal to what? T sin theta plus t1 sin alpha. Okay, t sin theta plus t1 sin alpha. Okay, and t1 you can find out from this. T1 is equal to t into cos theta divided by cos alpha. So remember there will be two arrangements. Okay, one is this, that is a suspension cable passes over smooth pulley, then this T and this T, that is tension in the suspension cable, tension in the anchor cable will be same, and there will be both vertical force on the tower and horizontal force on the tower will be there. Vertical force on the tower will be what? That is t sin theta plus t sin alpha. Okay, then horizontal force on the tower is equal to what? Horizontal force, this is t cos theta minus t cos alpha, and bending moment at the bottom of the tower is equal to what? That is this is horizontal, t cos theta minus t cos alpha into this h, that is bending moment. So for first arrangement, vertical load will be, vertical force will be there on the tower, horizontal load will be there on the tower, and bending moment will be there on the tower. But for the second case, okay, only vertical load will be there. vertical force will be there on the tower, and this will be T1 sine alpha plus T sine theta. Okay, and this T1 I can find out using this equation. This is a small expression, and these things you need to remember when we start with the problem. I hope you understood this problem, this small derivation. Okay, so in the next session now we're going to start with the problems on these conditions. Okay, so thank you very much for attending this session. If any doubt, please call me. Okay, and we'll meet in the next session. Thank you.